All right, so in this example, we have a bullet going and hitting a wooden block fixed in the ground. Bullet passes through the other side with a speed of 25 meters per second. If we ignore the small amount of gravitational potential energy, find the internal energy of the block bullet, and I should say increase in internal energy of the block and bullet after the impact. So why don't you go ahead and pause the clip here and see if you can think through this and work this out with your non-conservative work equation that's a little bit modified now with the conservation of energy, and give that a try. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so we're going to need our mass in kilograms for this bullet. And if we evaluate the energy, right, you have the kinetic energy starting out 255 meters per second. Then afterwards, that bullet continues on with 25 meters per second, but it slows down considerably. And because it slows down, that energy had to go somewhere, and that goes into increasing the internal energy of the system. So when we set this up, there's a small amount of gravitational potential energy change, negligible. So we can leave that as 0, and then we have our kinetic energy changing and relating to the change in internal energy. And so we've got the difference there, and we'll end up getting a internal energy increase of 805 joules. So that would be the increase in the internal energy of the block as well as the bullet itself too. So, considering all of the, internal energy increase of both of them. All right, so let's say we have a airplane that's landing here with an initial velocity or initial speed of 57 meters per second, and the landing distance, the time or the distance it takes for the airplane to come to a stop is 1,829 meters. And we want to find out what is the non-conservative work here, and then what's the force of friction. So we'll do that. So go ahead and pause the clip, and this will be good practice using that. And good review, and then when you're ready to check, you can hit play to continue. All right, so non-conservative work equals a change in gravitational plus a change in spring plus a change in kinetic, right? So in this case here, there's no springs involved, there's no actually gravitational energy involved, and so if it's flat, so we're just dealing with the change in kinetic energy, starting with 57 meters per second going to 0. So there's our non-conservative work, and therefore we have force of friction over that displacement, so we can figure out how much friction there was there. And so 1829 cosine of 180, right? Because the airplane is going this way, friction's this way, cosine of 180 degrees is -1. And so we have a force of friction of, let's see, 21,352.98 newtons. And then what is the increase in internal energy? Well, it actually is this, right? That's how much non-conservative work there was in joules. And so all of that non-conservative work, that friction there, went to increasing the internal energy of the system. Okay, so let's take a look at this situation where we have ice at -5 degrees Celsius, and we want to get it to steam at 125 degrees Celsius. Well, we know there's got to be multiple steps here because, we're going to be phase changing as well as increasing temperature. So if we have an ice cube at -5 and we're getting it up to 0 degrees, we have that here, and then the next step will be, once we get it to 0 degrees, we need to melt it. And then once we melt it, we can keep putting heat into it, going from 0 degrees to 100 degrees. And then once we have water at 100 degrees, we can phase change it. And then once we have, water or the water at steam at 100 degrees, then we can increase the temperature to 125. So I'm going to go ahead and we'll go ahead and set this first one up here. So, the heat required to get from -5 to 0 degrees. We have the mass 0.35 is the mass. We have the specific heat of ice, and then we have 0 minus -5, and so it'll take 3,675 joules to get that to the to 0 degrees. Now what I want you to do is calculate what is the energy needed to melt it. So this is fusion, latent heat of fusion. for this portion, the specific heat of water is 4186 joules per kilogram degrees Celsius. So you can figure out how much energy it takes to go from 0-degree water to 100-degree water. The next one is a phase change, so this is vaporization. And then the last one, we're going to increase the temperature Q equals MC delta T using steam. The specific heat of steam is 2010 joules per kilogram degrees Celsius. So go ahead and pause the clip and figure out these different ones along the way, and then you're going to add all of them together to get the total, and then that total will be the total amount of energy it takes to take this ice cube at -5 and then get it to water, or to steam rather, at 125. So go ahead and pause the clip and give it your best shot there, and when ready to check, you can hit play to continue. All right, so for latent heat of fusion, 333,000 times the mass, so 116,550 joules for that portion. MC delta T with the water from 0 degrees to 100 degrees, so 146,510 joules. From water to steam, latent heat of vaporization, 0.35 times 2,260,000 joules per kilogram, so 791,000 joules. And then lastly, for steam, increasing the steam from 125 degrees, well, to 125 degrees from 100 would be this. And so when we add them all up, we should get a total energy of 1,075,322.5 joules. So when we talk about the subject of thermodynamics, immediately comes to mind the idea of an engine. And so this is a picture of the Maid of the Lock steam engine ship that's still in operation as far as I know. And steam engines are more of a novelty now because, you know, they're not very efficient. They were the first kinds of engines that we dealt with, and they did great, you know, for the period that they have them. You know, the efficiency is very low for them, but they, you know, enabled us to do things we never could do before. And so in this clip that I like to show, there's a computer animation of this steam engine, this, you know, of this ship. And one of the things that it shows inside there is a piston, and inside there's actually two pistons. There's one above the other. What happens is, well, these are cylinders, and here's the piston. What happens is this gas comes inside, and when the gas is inside, this is the hot steam that's inside, so you could burn coal or whatever, and then as you burn that, you can heat up water. Water turns into steam, and you bring the steam in here. And it's ducted through in a specific way with this. And then what happens is this piston moves this direction. And as it does, it's moving cranks and then eventually moves the, you know, the paddle of the ship. But, you know, this hot steam pushes it this way. So it's doing work on it. Now, as it expands, this steam inside cools down. And then by the time it gets way over here, by the time this piston is over here, this gas inside here is cool, and then what happens is that you put more hot steam in here, and when you put hot steam in here, this pushes it back the other way, pushing this out the exhaust, and then this, you know, does the work and pushes it this way, and so it goes back and forth, back and forth, back and forth, and then turns the, you know, the crankshaft for the ship, and then eventually the pedals of the ship underneath. You know, another picture of this would be like with a train, you know, pushing the lever back and forth in the train, making the wheels go forward. And so that's the basic idea of a steam engine, and really the basic structure of engines are dealing with that. We have gases that are expanding that can do practical work, and that's essentially the core of thermodynamics. You've probably seen steam stacks like this, you know, where we produce electricity. You know, we're heating up water, which turns into steam. That steam turns a turbine. Then that turbine turns a generator, produces electricity. Over on the right-hand side, you have a picture of a train. And, you know, the hot steam is pushing the pistons, you know, back and forth and, you know, pushing the train forward. And so, you know, you see those older movies where you have trains like that, you know, And it really transformed life, or transformed our lives, the invention of the engine. And so the study of thermodynamics is that we can take thermal energy and transfer it into mechanical, actually practical work. And so all types of combustion engines, we're dealing with this, electricity production. So a huge deal here. Now, when we consider a thermodynamic system, we want to consider the system itself. And so this is the gas inside a container or a cylinder or whatever. We have a boundary around the system, and then we have the environment surrounding the system. And so for our system, we're going to be dealing again with ideal gases like the last unit, and considering the gas inside is an ideal gas. The boundary itself controls how the environment affects the system. So if you have an insulating type boundary, the system is going to be insulated inside and not affected as much. But if you have a very conductive boundary, then it can be pretty high, or the thermal interactivity can be pretty high. And so if the boundary is closed to mass, it means that mass cannot get in or out. And so with an open system, mass can enter or leave, but a closed system, mass cannot enter or leave. If the boundary is closed to energy, then we actually consider it an isolated system. And so these are the three types of systems we'll be dealing with here. So if we consider the Earth as a system, we could talk about what kind of boundary it has. And so if we consider that, the energy can be transferred in, right? So we get energy from the sun. So in that case, right, we're receiving energy. We're not an isolated system. The question is, are we closed or open? And so it depends on how technical you want to be, right? Because, technically, sure, we lose some mass, we gain some mass, but it's not on a very large scale. And so, you could probably argue either way there, right? All right, so in the thermodynamic process, we can be changing the pressure, temperature, or volume. And then, if we're looking at that, the gas itself can be doing work, or work could be be done on a gas. And so we have both of those situations in a thermodynamic process. If we consider back to our steam engine, right, we have that gas that's expanding and it's pushing that piston over. As it does, it's actually doing work as it does that. So, if we have a frictionless cylinder here with the piston, piston can be moved up and down, so work is done on the piston, and so the gas can also do work on the environment. So this this idea of using this cylinder with a piston that can move up and down is a really helpful way of example that we use pretty extensively here in thermodynamics to evaluate what's going on with the gas and how it's affecting the environment, or the environment's affecting the system. Now, if we consider this gas inside, and let's say we have a certain force that's bringing this piston down like this, right, over a certain distance. Well, if we multiply and we look at work, right, work is force times displacement. If we multiply area over area, which is essentially 1, right? So this area right here, the area of the piston, area over area, we know that force over area is pressure, right? So however much force over that area is going to be a certain amount of pressure. And then D times A, right? If we take the area times the distance here, we actually get the volume, right? And so what we can get here is, with work, we multiply the pressure times the volume, and that will give us, how much work is done on the gas or by the gas, depending on which way it's going. So if we draw that out, right, we can put this on the side, and let's say that the gas is doing work. So what happens when the gas does work is that the volume expands. And with that volume expansion, we, delta V there, we have a certain amount of pressure times the change in volume, and we can figure out, the work done by the gas. And in this case, the positive volume change means that we'll have positive work. If we have work done on a gas, that means that the volume is getting smaller. And if the volume gets smaller, work done on the gas will have a negative, it'll be negative. So the change in volume is negative, and we have that. So let's go ahead and take a look at this with M1. Calculate the work done by a gas that expands from 0.02 meters cubed to 0.8 meters cubed at standard atmospheric pressure. So yeah, go ahead and try this one here. Go ahead and pause the clip. You're using pressure in pascals here, so we want to do that. And so yeah, go ahead and try that. And when you're ready to check, you can hit play to continue. All right, so the the volume is expanding here. We have the constant pressure, 101,000 pascals times the change in volume. So it's going to be positive work. The gas itself is doing work, going, the volume is increasing. So this would be 78,780 joules. In this one, we want to find we want to find the work done by a gas in a cylinder that expands by 5 centimeters. The radius is 2.5 centimeters, and the pressure inside is 1.5 atmospheres. And this one, we're going to have to go back to where we're looking at the different, the areas and the displacement and all that. And so, yeah, why don't you go ahead and pause the clip and try this one, and then when you're ready to check, you can hit play to continue. Okay, so we have our piston, and it can expand 0.05 meters, and so pi r squared is the area then, and so the area of that is 0.001963, and so the volume we can find by the area times the displacement there. So this will be the volume change, and this should be in meters cubed. And then when we look at the pressure, we have 1.5 atmospheres, so that'd be 151,500 pascals. And the total amount of work done then is 14.87 joules when we multiply the pressure times the change in volume there. And it would be positive work because the gas is expanding. So when we looked way back at motion graphs, so let's say we had a car that's going here at 3 meters per second, and let's say it goes for 10 seconds, right? Velocity equals displacement over time, and we have 3 meters per second. And go for 10 seconds. So let's say the car is going to go 30 meters, right, from here to wherever. So if we look at this graphically, position time, and well, not position time, velocity time. Okay, let's say it's going 3 meters per second, and it's going for 10 seconds. So that's what the graph would look like across here. Well, 3 times 10 is 30, right? So if we have velocity on the y-axis, time on the x-axis, what is actually going to give us the displacement? Well, it's the area. It's the area underneath the curve here. Will give us 30 meters. So 10 seconds, 10 is how long here, then 3 meters. So we have that. We did the same with work, right? We had a force displacement graph. And then whatever that area is, we know work equals force times displacement. We're multiplying those two things, x and y axis, multiplying those two things. This area will give us that value. Over here, velocity and time, that area will give us that value, right? So when we look at work done by a gas, we're dealing with pressure and volume, right? We're multiplying pressure times volume, and that's going to give us the work. And so, in this picture here, we have an example where we have a gas. Let's say that, we have a certain gas and the pressure is just dropping, but the volume is staying the same, no work, right? But then once you're at this certain pressure and your volume expands, this area underneath here will give how much work that you have. How about here where we have a certain amount of pressure? Well, if we have a certain amount of pressure and the gas expands, we go this way. And then if the pressure stays the same and the volume, or the pressure drops, but the volume stays the same, it just goes down. This entire area will give us how much work we have. And in this case here, let's say we have a certain pressure, and as the volume expands, the pressure drops a little bit. It's just, again, the area underneath would give us how much work is done. So likewise, in this picture, if we consider, a gas that, let's say we have a certain amount of pressure, it increases, decreases a little bit, all this would give us, you know, how much work is done. Now, if though, let's say, and this would be what kind of work? Well, the volume is increasing, right? The volume is increasing, positive work. But if this gas, you know, is compressed, right, going from a higher volume to a smaller volume, and the pressures are changing a little bit, this is actually, this area here is negative work, and so the resultant, you know, the total amount of work would actually be this inside the little oval here.